Right, so here I'm going to go through 1.2, the last part, which is the assembly language part in Little Man Computing. So obviously assembly language is a low-level language often used today to program device drivers, but even then it would mostly be the bits that are repeated like a graphics card or something, over and over again. Or to do simple microcontrollers, although again, many would be written using C. Or other languages now. But anyway, it has a one-to-one relationship with machine code. So for every machine code instruction, there will be an assembler mnemonic. So if 45 is load something into register, there might be a load or a LOD. It's normally got 3 or 4 letters mnemonic, but it can be different. When you create assembly, it is unique to that processor series because obviously each mnemonic represents a number in machine code that might be different on a different CPU. So you can't just write something in assembly and it work for everything. Now, they are similar, but if you're doing something complex, it probably wouldn't work. But you'd need to sort of program it for that series. So if you're writing something, I got bored during the pandemic and wrote something for an old Atari. I can't just run that on another computer. It's for the Atari. I use the Atari instruction set. I can't remember it now, but it was Pong I made, basically. But anyway, so yeah, I mean, it's a bit of fun to play around with. So Little Man Computer is a not real computer. It's invented to help teach, and it's got these massive number of instructions. All of, on how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 instructions. Well, it models a simple von Neumann architecture, and it's just used to teach. You are expected to know these mnemonics and what these instructions do. So I'll just go through them. So you've got load, which was LDA. And that copies what I'm going to say variable, but it's not really a variable, but it does act like a variable. It's just a data in a memory location, but you could argue that's all a variable is really. Into the accumulator. Store does the opposite. It stores something in the accumulator into a variable. I'm going to say variable from now on, but add will add what's in a variable to the accumulator. Okay, so it won't store it in the variable. The variable will not change, but what's in the accumulator will be increased by what was ever in that variable. And subtract does the opposite. Input allows someone to type in some data and it will store it in the accumulator, not in a variable, in the accumulator. You need to store it in a variable if you wanted to input and then store. Imp STA. Okay, output prints things out from the accumulator. End obviously stops the program, which is halt. Okay, you branch if 0, so that will do a loop. Well, not loop, it'll move back to a previous part of the code if what's in the accumulator is 0. That will do it if it's 0 or positive, and that will always branch, doing a forever loop, unless you branch out of that loop. And this is just how you set up a sort of variable called data storage. Now let's have a look at a basic one. I actually asked ChatGPT to create one for a bit of a giggle. So the main issue with writing Little Man computer programs is to remember that everything goes to the accumulator. So you have to move data in and out of it a lot, and it can be easy to forget this. So let's look at this program. Okay, we get input and that will be stored in the accumulator. Okay, in fact, I could run this and show you it over here. Actually, I could do that. But just very quickly, I've got a online simulator. So we've got imp, we've got STA num1. Now, I'm actually going to say that this version of ChatGPT did not do a very good job. It actually, well, I didn't do a terrible job. It does work, but it doesn't. It pointlessly stores the data that it doesn't need to, and I'll get to that in a second. So let's run it. So this program is to add 2 numbers together. Okay, so we do 5, we do 9, and it outputs 14. Okay, and so let's go through the program. We get input and we store that in the accumulator. Okay, then we go, right, we want to store that somewhere, so we store it in num1. We set up num1 down here. You could call it a variable. Then we input num2. Well, you input the second number, sorry, and we store it in num2. So now we've got num1 and num2 stored in here. Okay, in these memory addresses over here. In fact, you could see where they are. They'll be, if I maximize this, they'll be here. Look, I typed 5 and it's stored in 8 and 9, and you can see the gap. It's even used this gap to have no, So then it reloads num1 back into the accumulator, adds num2 to it, and then outputs the result. So it loads num1 back into the accumulator, adds 9 to it, and outputs the result. Now, actually, that's inefficient because there is no reason to store num2 at all. Once we input it, it'll be in the accumulator. So I then actually asked, I spotted the mistake and was like, can you improve that, ChatGPT 3? And it did the correct version, which is here. Because there is actually no reason to ever store number 2. So I'll show you the reasoning behind it. Because why are we loading back number 1? That is actually the program there, and it does the exact same thing as before. So if we type 9, 15. Well, I did 9 and 15 this time, so I did 24. I can't remember what numbers I did last time. But that's correct. So if you think about it, we get input and we store that number in number 1. We get the second input, and now that's in the accumulator. Okay, so there's no reason to store it in number 2. We only want to add right now. Okay, so then we add what's in number 1 to this number they just typed in, which we'll call number 2, but we're not actually storing it anywhere. We output and stop the program. So yeah, so that's actually, it could be quite interesting. I wouldn't be surprised that's sort of an exam question here. They could show you this and say, might not ask you to rewrite it. They might do, but they could say, what's an issue here? And if you just don't quite get it, the reason is that when you do add, you add whatever this is to what's in the accumulator. And input gets input from the keyboard and store it is in the accumulator. So what is the point of getting the second number, storing it in num, and then reloading the first one? Because what this is doing, it's sort of doing num1 plus num2, but mathematically num2 plus num1 is the same. So there was no reason to sort of pointlessly reload num1 and then add num2. Okay, you could have just added num1 here to number 2 that you typed in there, and there's no reason to even store number 2. So that's basically Little Man Computer. There's lots of tutorials on it online, lots of examples and other stuff. I will do an exam question in a minute that I haven't practiced. Right, so I wanted to show you a program that had 2 things. One of which, how do you set a variable to have like a constant, really? I'm making a constant called 1 with an initial value. So here I haven't got to get him to type something in for that variable. It's just stored there. And second of all, how do you do a loop? So let's have a look at this program in the Little Man Computer. There's no point having that open. So what this program is going to do, if you can see here, I'll run it. I'll write a number at 10, and it's going to print 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and how does it do that? So let's have a look. Well, we get input from the keyboard, obviously, and that is now stored in the accumulator. So 10 would be in the accumulator. Then this loop, by the way, is a tag. I could call this P for any intensive purposes there, all intents and purposes, and it would still work. As long as I don't use something that's already got a name, like BRP or halt. I can use anything. I could use loop 1. Obviously, people tend to use loop 2, loop 1, loop 3. But if you had a section that was like you're doing something, then I would name it something, correctly. But here's just a loop. So that is just a tag for that line. Okay, so that just means we're going to go back to here. So we output the number. So remember, it was, let's say it's 6 because it's a low number. So we input 6 and then we output 6. So we input 6 and then we instantly output 6. Then we sub 1. Now remember 1, again, I could have called this O or anything. It doesn't have to be 1. It's only a 1 because I put 1 here. If I put 2 there, then we would do it in 2s and it would go 6, 4, 2, 0. Okay, but obviously I'm going to count down in 1. So that's just setting the initial value to it. Okay, so then this is branch if positive. So let's just rerun it and I'll do a nice low number like 3. Right, 3, 2, 1, 0. So we output 3, we deduct 1 from the accumulator, and then we check the accumulator to see if it's a positive number greater than 0, basically 1 or more. 3 is greater than 1 or more. It's greater than or equal to 0. Branch positive is 0 or greater than, right? That's key in a minute. So if it's greater than or equal to 0, right, then we go back up to loop, which it is. And so 3 is greater than or equal to 0, so we output, 2 is greater than or equal to 0, so we output 2. Then it goes down to 1. 1 is greater than or equal to 0, we output 1. It goes down to 0. 0 is greater than or equal to 0. We output 0. We take off 1. It's now minus 1. You can see here, the accumulator ends up on minus 1. So that is not greater than or equal to 0, and we slip through into halt and finish. Now, what if I didn't want to say print the 0? Okay, there might be other ways to achieve this, but what I could do is there is actually a branch if 0. So that's BRZ. Now I need to do something, and because this is going to be end the program, I'm going to call it end. Then I'm going to tag the line halt with end. So now, if before we check if it's a positive number greater than or equal to 0, we can check if it is 0. And if it is, we skip that by branching over it. This is a concept quite common in this little man computer about branching over branches to have these situations, because I don't know if they do it deliberately to be awkward or difficult, but they only have 3 branches. Branch always, branch if positive, branch if 0. It'd be good if it was like branch if greater than a variable. Then they do have these in real computing, but I think it's deliberately challenging to make you have to think about how you would solve a problem. You know, that's the whole point of it, to make you try and really think about how you solve something. So here it won't print the 0. Oh, it did. What did I do wrong? Branch if 0 end. Oh, I didn't load it. Sorry, you got after you make changes, you must click load in here. Now that can, I have sat there for a long time. I remember I was doing an exercise in the class for about 10 minutes and I was like, why is mine not working? I just forgot to click that and it's really irritating. But there you go, 3, 2, 1, 0. So just think it inputs 3, it outputs it straight away. Okay, then it takes 1 off it. If it's 0, we branch to the halt. Okay, if it's 0 or more, but obviously at this point it just means greater than 0 because we already leave if it's 0. We go back up to the top and repeat 3, 2, 1. Okay, so there's lots of videos on the little man computer that you can look at online, and lots of activities and exercises and whatever. Yeah, so I won't go too much into that because you can learn it anywhere. So where was I? Right, addressing mode. Right, now. Okay, this is the bit. This is the bit. Because little man computer uses direct addressing mode. Now, what that means is that you're giving a memory address when you load things. So if we go back to the program here, when you do, there's one that loads. When you do, well, it doesn't load it back, but or store, both store and load do work the same way. You're actually giving it a memory location. This is a memory location. That's why I'm not calling it a variable, right? It's a memory location. And you're storing it in that memory location there. Right, if you go back to the program, let's just do something pointless like this. So let's do this. We'll do num that, and then we'll do sta num. Okay, load the program, click run, hit 5, and then we store it. So this is sort of 2 because it's there, and so this is basically, this num means memory address 02. So when you're talking about loading and numbers, and let's just do add 1. I'll do 1 that 1. Okay, and then I'm gonna reload num1, right? So that's going to add 1 to it and then reload it. Now we can actually step through this if we want to. We can put this speed really low. That's really low, yeah. So let's go 5. So moving 5, it add 1 to it. Oh, it's too quick. but I wonder if there's a way to step through it. Oh, there is. Like this. Oh, okay, let's reload it then and do that. So let's do 5. Okay, so 5 is in the accumulator. Now we're going to store it in num. Now num is 1, 0, 1, 2, 3, 4, 5. So it's here. No, it's 4 because it must have deleted that. 0, 1, 2, 3, yeah. So we go next. Bang. So it's going to store it in there. It's removed the line. I shouldn't do that anyway, really, to make it thing. So let's do 4. Okay. So this is called direct addressing mode, right? Direct addressing mode. So hard to remember. Right, so we're running through. So now it stores it in address 4, right? Then we're going to add 1 to the accumulator, and now we're going to load the data back from address 4. 4 goes back in there because it's stored in there. So this bit here is a memory location, okay? Now, I don't know if you can actually do 04. I don't know if that's actually possible to write that. I don't know if it'll allow you on this system. It might. I don't know if it'll let you, but it's a memory address, okay? So when you do load and stuff in the little man computer, it always uses direct, which is that you load a direct one. So let's just look at all the 4 ones and explain it better. So immediate would mean the actual number. So we can't do this in little man computer, but if we write 67, that's not going to do anything. I don't know why it's asking to I still haven't done load program. It's going to, no, not work. It's gone 5, 6, 7 and nothing's happened. Probably if I type number in there, it probably actually load that. Well, the accumulator's now got 34 in it for somewhere. Yeah, because I wrote 34, you see. So that is a memory address. A memory address. But immediate would actually load 67 into the accumulator. So immediate would load the actual number in there. So this is the data itself, right? The operand is the data. The instruction would say load 67 into the accumulator. Direct is what we've done. Okay, so if this was our memory location, they're often denoted in dollars. They're all in binary, but I'm just using hexadecimal, right? So this one is a memory location. So this would load 9 because 9 is stored in that address. That's what happens in the little man computer. We just saw that. I typed 67, it doesn't load 67, it loads what's stored in 67, and I typed 34 in there. So it loaded 34. Okay? Now, indirect is that it's a really weird one. It's like, I should probably put dollar there. It's an address of a place that it's basically like this twice. It's an address that holds the address of the data. Now, this is normally because a register is holding the address of the data. And so you're saying, right, that register at this address holds the address of the data. Think of moving twice, right? I'll do it by example. So we go to $AF3 that has an address in it, and that address has the data. So you can sort of think of it as direct twice. It holds the address of the data. That holds the address of the data. I know it's a tricky one. The reason it's used is often because sometimes a register will be like, oh, here is the address of the data they're accessing. And so you're like, oh, look in that box, because that's the box that's storing where we're storing stuff. I know it seems strange, but that's it. Okay, that's what indirect is. It holds the address of the data. Okay, so AF3 holds the address of the data. Weird. Now, index is an offset. An offset meaning like you go down. Think of it as an array. Well, arrays do use this, right? So you've got something called an index, and that will hold a starting address. Okay, so with index addressing, there'll be a starting address. So let's say we've got some sort of memory that says that AFF3 is our index. So where 0 is here. And then a register, like in this case R0, holds a number. And that number is an offset down memory. Okay, so if it was 0, the actual data would be this. This would be 1, this would be 2. And this is basically how arrays work. It's why arrays are what's called contiguous, which means that in RAM, all the data is stored in a row because it speeds up access. Because if you want the 10th element, you can use index addressing, set that to 9, would it be 9 actually? Because the 10th one would be 9 because 0 would be the first one, right? But you set that to 9 and you'd get the 10th one, just like in an array. So you can think of it as an array. There's an index that holds the starting address, okay? And then when you do load and you give the operand is the offset. How many down from that memory location, right? So, tricky one, but let's get through it. So let's have a look at some exam questions, right? I've got this off a real exam paper, and just to avoid, I'm just going to say I don't particularly like this question. That's a bit of critique and review there. But anyway, so little man computer assembly language is stored in memory as shown in figure 3.1. In this variant of LMC, because it isn't the real one, the symbols ampersand and hash are used to denote different modes of addressing, which we just looked at. Given the output is 17, state the addressing mode represented by each symbol. Right, so it loads something, it adds something to it, and it outputs it. So we need two numbers that add up to 17. And we've got essentially quite a few ways of getting those numbers. You've got 2 and 15 add up to 17. You've got 7 and 10. You've got 4 and maybe other numbers. So let's have a look at what load 7 could be. Now, bear in mind the 4 addressing modes are immediate, direct, indirect, or indexed. It's very likely one of them is going to be immediate. I actually haven't looked up this answer, by the way, just doing these live. It's very likely the two most used ones are this one or this one, but it could be this one or this one. It's very likely to be index because we need some sort of index. Where's the index been set to? We'd have to say like index starts here because where is the index? So we can sort of rule out this one because we'd need to know what the index is. And it doesn't look like it shows us that. And it's the most complicated one. So it's probably one of these three, right? Immediate, direct, and indirect. So I just try it out. So if it was LDA7, let's try dot. Let's try. I always think try immediate first of all, right? So let's say we load 7, because if it wasn't, let's try delta Z. If it was, it can't be indirect for the first one because it's 15. So it can't be the address of the address because we can't see 15. So it's either the value 15 or the value 7. Okay, in this one. So the first one we know is either immediate or direct. Okay. Now it doesn't take a genius to work out that if it's 15, right, then it would have to be 2. And looking at 4 holds 6, 6 holds 10, and 4 isn't 2. So we would need 15 plus 2. So we'd need 5 or the number 2 to be involved here, and it's not. So I can pretty much assure that that one is immediate, meaning that it is literally loading the 7. So I'm going to put that in because I'm sure that is immediate. Because it can't be the others, because if it can't be the address of the address, because that's 15 and that's not on here. And if it is the address of the data, then we've got 15 and we need 2. And the only places I can see 2 are here. So we need either 5 here to be the address of the data or 2 here. Now it could be an offset, 1, 2, 3, 4. Now that is tricky, but we don't have the index to know that that's a 4 offset. So that seems a bit unlikely. So let's just take that we've loaded 7, okay? And then we need 10. Now I look and see that 10 has got the number 6 next to it. And that looks like that one. So I would say that that is immediate and the second one is direct. So immediate has the actual number and direct, because that is going to add what's the address. That holds the address of the address, sorry. No, it's not going to be. It's going to be indirect. That's going to hold the address of the address, because that's got 6 in it. We don't want 6, we want 10. Yeah, so that's got the address of the address in it. And so, yeah, there we go. There we go. That's how you got to work out. It can be tricky. Okay. So that holds the actual number and that holds the address of the address. There you go. 7 and 10. I know that's tricky. Easy to make a mistake there. But there we go. I'm pretty sure that's right. I will pause the video and check. Yeah, it's correct. I just paused it and checked. It's correct. Right, so now let's do this one. Write a program to allow the user to enter numbers until they type 0, then you output the total of the values. Right, so I'm going to do this live, so if I mess it up, apologies. So let's get it to the side here. So we want to get them to input numbers until they type a 0. Right, so we're going to need to loop back to the input. So I'm going to call it loop, and I'm going to get input. Okay, until they type a 0. So it's going to loop. So I'm just going to branch to loop. Okay. So I'm going to branch to loop. So now I'm going to run the program, and it's going to ask me to enter numbers. Oh, there you go. Right. Now I need to. Oh, I can't get out of the program. Can I stop? There we go. Now I need to make some sort of total, running total. So I'm going to store it in total. Just quickly, I'm not saying this is correct. I'm just working it out. So I'm going to do it lowercase. So I'm going to do total that, right? And so we're storing it in total, and then we're going to load the program, run the program. You should see 6 stored there. See 7 stored there. Right, I'm going to cancel this and stop. Right, so now we need to add. So when they input something, we're going to need to add it to total. But when I load total, I'm going to lose what they've typed in. Oh, I don't need to lose what I type in. I just need to add total. So I need to add total to input and then store it back in total. Right, okay, yeah, that makes sense. Because we're getting them to type in a number, then we add it. We're going to add what's stored in total. I might want to start total at 0 just in case. I know it's 0, but I'll start total at 0 just for, it looks more like proper code, right? So I've started total at 0. Whatever they type in, I'm going to add what's stored in total to what they typed in and then restore it back in total and then loop. So if I load the program and run it, we're going to type 5 and we should see 5 in the accumulator. Bear in mind, this is the memory address you want to look at. So 11, and then that should turn into 16. There we go. 1621, and we should get 37. Yeah, and so total has now got our running total, right? Brilliant. And it's also in the accumulator, so there's no need to load it back. It's already in the accumulator, right? So now I need to, if they type a 0 in, I need to quit, right? Stop. So what I'm going to do here is I'm going to do end. I'm going to output, and then I'm going to output. Now the problem is they'll have typed in a number. So because they'll have typed in a number, I'll actually do it. I'll do that. You might think it's that. And you might write that and think, yeah, we're getting there. And then if they type in a 0, we branch if 0 to end. Okay, so we get them to enter a number. If they type a 0, branch to end. We output and halt. But here's the problem. This won't output the total. It'll output 0. So if I type 5 and then 6, now annoyingly I can't see the address now. Let's maximize it. And then 7. So we've got 18 here, right? Now I'm going to type 0, and you think it's going to print 18, but it will actually output 0. That's because I've just typed in a number, and that's in the accumulator. So what I need to do there is, before I do it, is reload back total. Okay? So I do 5. Now this will be a tough exam question. I made this up, by the way, to be difficult. Okay, so 4. But I think I think it's doable, at least to get quite a few points. I mean, it might be edit, but I'm just showing you one. There we go. I'm just going to type 0, and then it will output 12. Here you go. Slowly, because I put the seed really low. And I typed 543, which, hold on, yeah, adds up to 12. For some reason, my brain had, I was like, no, it doesn't. But it does add up to 12. Hurrah! So yeah, that's basically it for this section. There's lots of stuff you can learn about the Little Man Computer online, but I'll stop there.